Welcome to this lesson on one of the most commonly asked about aspects of the GMAT rates and work problems. So let's just dive in with what the basic rate equations are. First, we know that the standard distance equation, and this is how most people remember it, and sometimes you'll hear the acronym, or I guess the eponym of DIRT. So that would be distance equals rate times time. And you can also extrapolate that to work is equal to rate times time, as you see on the screen. Now, you can rearrange this equation to solve for the other two pieces, rate and time, as well. So we know that rate is going to be equal to the work or distance divided by time, and time is going to be equal to work or distance divided by rate. And the GMAT does really require you to be able to rearrange these equations pretty seamlessly. So let's talk about how these values relate to each other proportionally. So first, always confirm that the rate is listed as constant. This is a relatively cheap trick that the GMAT doesn't do a whole lot of, but sometimes they won't tell you that the rates are constant and you can't assume anything. Because if the rates are not constant, then we don't know if Jimmy went out and worked for an hour really quickly and then didn't work at all for the remaining 5 hours as described in the problem, or if Jimmy consistently completed the job. So you do have to make sure that they say that the rate is listed as constant. So if you keep your time constant, if you increase either your work or your rate, the other variable will increase as well. This is what is known as a direct relationship. So for instance, if we had 20 units of work that were to be completed in 5 hours, the rate would be 4 units per hour. But if we increase the work, we have to increase the rate. So if we keep the time constant at 5 hours and we double the amount of work completed to 40 units, we double the rate as well to 8 units per hour. Now, if we keep the rate constant, if we increase the work, we'll also increase the time. And this, again, is a direct relationship. So using a similar scenario, if we have 20 units at a constant rate of 5 units per hour, that's going to take 4 hours, 20 divided by 5. But if we double the amount of work from 20 units to 40 units, we then have to double the amount of time it's going to take if we keep the rate constant at 5 units per hour. And then we get to the tricky proportion, which is between rate and time. And this is what is known as an indirect relationship, because if you increase the rate, you have to decrease the amount of time it's going to take. Because if you've got a faster amount of completion of the work, you're not increasing the time, you're actually decreasing it. Now, if you have a constant amount of work of 20 units at 5 units per hour, the time is, once again, 4 hours total. But if you were to keep your work constant at 20 units, but double the amount of units you completed per hour to 10, you have the total amount of time that it will take. So you'd have 20 units at 10 units per hour, only taking 2 hours. So you can see as the rate goes up, the hours go down. So all of this is going to be the key to everything we do moving forward. So we have a rate problem example here. And so, as always, we're going to set up the scratchpad listing the choices vertically from A through E, and then we're going to skip to the end of the problem to identify the sought value and label the choices as such. And we can see we are being asked, how many more hours would it take those remaining workers to complete the order working at the same constant rate? So label over top on your scratchpad, number more hours to complete, and then we have to begin reading it. So we read from the beginning, taking notes and setting up calculations as we go. So we discover that 6 workers working at a constant rate at Bill's Widget Emporium are able to fill a certain standing weekly order for a number of widgets in 20 hours. If one of the workers called out sick for a week and only 5 workers were available to complete the weekly order, how many more hours would it take those remaining workers to complete the order working at the same constant rate? So we'd be taking our notes, and we know that from the equations we just saw, work is equal to the rate, and in this case, it's represented by the number of workers times the time. So we can set up an equation of 6 times 20 is equal to 120 units. And generally, we know that It's best if you're looking at algebra technically to probably get to the end here before you start working through things because they can always throw a curveball in these lengthy word problems. So, but we now know that that's the total amount of units that would be done here. So in order to find our new time, we've got our constant amount of work because that standing weekly order does not change of 120 units, and we've got to divide it by the new rate or number of workers because the number of workers impacts the rate. So our new rate is going to be 5 workers once one calls out sick. So our new time is going to be equal to 120, the constant work that we defined, divided by the new rate of 5 workers. And our new time is going to be 24 hours. But remember, we were being asked for the number more hours, so don't pick 24 at this step. Instead, remember, you've got to take 24 minus the 20 and say that it's going to take 4 more hours. So this is our technical rate solving process. Let's consider another way that we can consider rates, which is through a ratio table. So here we're just going to talk about an abstract scenario where we've got a fruit basket and we've got apples and bananas, and those are the only fruits in our basket, and we've got our total fruits. And on the left-hand side, you're going to keep track of your ratio and your real values through 3 rows. So you've got your ratio, which is going to be the defined ratio, a simple concept mathematically. You're going to have your constant multiplier that is going to then be used to get to your real values and keep track of everything visually. So to use the table, we know that the ratio values and the real values sum to our total parts. So in this case, if I said that we have a ratio of apples to bananas of 5 to 2, we know that our total parts of the ratio, our total fruit minimum, is going to be 7. In GMAT world, you're not going to have a fraction of an apple, you're not going to have a fraction of a banana, and of course 5 plus 2 is 7. So if we just hypothetically filled in some real values here, we see that if I said I've got 25 apples, then I've got to have 10 bananas, and we'd have 35 total pieces of fruit, and this is all proportional. Why is that? So it's because the multiplier is a constant for all columns in this table. So we can divide any of our real values by the corresponding ratio value in that column to find the constant multiplier for the table. So if we divided 25 by 5 or 10 by 2 or 35 by 7, we discover that our constant multiplier is going to be 5. And if instead we've been given, say, the multiplier in some fashion here, you can always multiply the ratio value by the multiplier to solve for any real value columns that you have. And you can always expand this total out, or this column out, to say 3 values, 4 values, whatever it may be. Always make sure, though, that you include a total value at the end, at the far right of your table, to make sure that you don't say something like the ratio of fruits. There are 5 over 2 fruits in this basket. No, you've got to make sure that you account for the bananas in your total as well. So this ratio table can actually be used to solve for a rate. And here, you've got the exact same problem, right? So we're just saying we've already done the work. We've already set up the scratch pad. We've got our identified value we're seeking. And we can set up a little partial ratio table for the information that, 6 workers were working. We've got 20 hours as our time, and we're going to go down to 5 workers ultimately. So here's our little table. And we know that our workers represent our rate, and our rate is going to go down. So that means that our time proportionally is going to go up. So first off, again, logically estimate to eliminate any impossible choices. Here, 24 is definitely not it, because right now it's taking us 20 hours and we're not going to more than double the amount of time just by removing 1 worker. So always look to logically estimate. If you weren't able to do it the technical way, here you could just say, even if I'm completely lost at this point, get rid of 24, because we know that it would require more than having the number of workers, because doubling the hours and having the workers we know is a constant ratio that we in direct proportion that we can rely upon. So then we have to consider what is that multiplier from 6 to 5, because we know that our new real value for the workers is 5. And that's going to be 5 6, because we just take that 5 divided by 6 and know that that is our constant multiplier. But because we have an indirect ratio, we've got to use the reciprocals to account for that indirect relationship. So instead of multiplying the hours by 5 6, we've got to multiply by the reciprocal of 6/5. So then we, as always with fractions, divide by the denominator and then multiply by the numerator to find that our new total is going to be 24, because 20 divided by 5 is 4. 4 times 6, 24. And of course, don't forget our last step again here. 24 minus 20 is 4 more hours, and you can see the big old trap that was laid if you were using the table. If you're not careful and you solve for the wrong thing, you'll pick 24. Always logically eliminate as you go to avoid those types of pratfalls. So we're not done with different ways you can address rates, though. We can also use a rate circle, which is basically a cousin of the average circle we discussed in another of these lessons. So your rate circle is going to be a visual representation of that DIRT equation that we talked about. So worker distance is on top because you can take your time and multiply it by the rate to get your worker distance completed. Any two values in the circle can solve for the third. So if I've got work and rate, I can solve for time. If I've got time and rate, I can solve for worker distance. If I've got work and time, I can solve for rate. It's just, again, a nice, easy visual representation of the three different equations that we started here with in this lesson. Now, you can, just like we do with the average circles, use multiple circles to coordinate complex rates. But you have to be careful, just as you are with averages, add or subtract the raw work totals, the raw distance totals, or the times, but avoid doing it for the rates. Because if you try to add or subtract rates, you may not appropriately account for the weighting of said rates. So this is our rate circle, the cousin to the average circle. So we have the same problem yet again, and this time we're just going to consider this as our quote-unquote alternative tactic process. Because let's say you're reading this word problem and you're like, I don't really see what's happening. And that's okay. You're still going to begin by taking notes and setting up calculations as you go. So we've got our workers, it's 6. We've got our hours right now, that is 20. We've got our new workers, which is 5, and even if you're completely kind of unfamiliar with rates, you know we've got to figure out the new hours in order to get to the sought for value, which is how many more hours it would take. So that's our big question. What are the new hours and how do we get there? So at this point, you might note some possible alternative tactic clues. First is the word certain. And we remember that certain, along with in terms of and unknown, are indicators of potentially plugging in easy values to model. We also have an unknown value dictating the entire problem. In this case, it's the number of widgets in that standing weekly order. So because of these alternative tactic clues, you might recognize that opportunity to model the scenario. So let's consider how we can model this rate problem. So once we've identified the tactic clues, set up the problem as normal, we need to set an easy total value for the unknown number of widgets in this quote-unquote certain order. So we can just consider the product of the given values as an easy total. So we know right now we've got 6 workers, we've got 20 hours, so let's just say it's 120 units of work, units being an anodyne metric that you can just use. You'll also recognize that 120 happens to be the key to the technical approach as well. But here it might be a little bit more intuitive for those who are less algebraically inclined. And if we go with 120 units, we know that that results in a given rate of 1 unit per worker per hour. Because we've got 20 hours, we've got 6 workers. So each of those 6 workers is going to be responsible for 120 divided by 20 hours, 6 units. And so that's going to be 1 unit per worker per hour. So it's just the simplest conversion rate, kind of like in an analog fashion. So then we set up a rate circle for our new rate of 5 units per hour using our modeled number of 120 units that will be our constant work for the standing weekly order. Then all we have to do is divide to find the time using the rate circle. And of course, 120 divided by 5 is once again 24. Beware of that trap of 24 exactly, skipping that final step of figuring out how many more hours. But then, of course, 24 minus 20, once again, is 4. So these are the 3 primary tactics that you can use to solve for a rate in the GMAT. And you can see there's different ways of combining rates and all those sorts of things. Consider which is most apparent to you in the moment. That's going to be key. Now, there is one more concept with GMAT rates that we want to talk about, and that's going to be combined time. And this is just a simplified formula that is probably worth memorizing, because we know that the time it takes worker A, we'll just use worker or machine, whatever it may be, times the same time or the same metric of time for worker B divided by the time for A plus the time for B is going to be the combined time that it takes the two when you set them up together. Just because this is the simplification of like combining the rates. So to use the formula, it is just a simplification that you're probably going to want to memorize. You'll also want to make sure that you confirm a consistency of the metrics that you're using. It's got to stay minutes in all of the times. It's got to stay hours in all of the times, days in all of the times. Make sure that you don't conflate metrics and only use it for combined time. If you're going to try to combine rates, probably want to use one of the other tactics that we just used. Or vice versa, we don't necessarily want to use a ratio table when we're doing combined time because it's not the exact same methodology for solving. And so those are the main concepts that underpin all of these honestly frequently tricky rate problems that you'll see on the GMAT. So let's go ahead and move over to the whiteboard and take a look at how we can apply that combined time formula in a problem solving example. Okay, so let's go ahead and take a look at this scenario. And as always, set up the scratch pad A through E with a little spot over top for our sought value. And you can see we've got simple numbers here, so we might as well just write these out at the outset. So got a couple of mixed numbers. Don't know what they mean yet, but that's certainly coming. So we skip to the end and we see that we're being asked, in how many hours can a single standard photo order at Jabba the Photo Hut be completed if the two women work together at their respective constant rates? So the number of hours is what we're being asked to solve for. So we get the information that Jenna and Bella are each available to print a standard order of photos at Jabba the Photo Hut. If Jenna can print a standard photo order in 6 hours, so J time is equal to 6 hours, and Bella can print the same standard photo order in 3 hours, so that means that our B time is equal to 3 hours. We are then being asked for the combined time. And this is where that equation that we were just talking about makes this really simple if you can recall it. So we know that the combo time is equal to the time A times the time B all over the time for A plus the time for B. So in this case, we're just looking at our combo hours being equal to 6 times 3 over 6 plus 3. And that, of course, is going to just be 18 divided by 9, which is equal to 2 hours. And our answer is choice D. Now, that's what we do if we remember our combined time formula. Let's say in the moment we just didn't remember it. Well, we still have a way to work through this. So again, setting up our answer choices A, B, C, D, E, and we've got the number of hours. So again, 1/2, 1, 1.5, 2, and 2.5. So we know that Jenna and Bella are available to print a standard order of photos at Jabba the Photo Hut. If Jenna can print a standard photo order in 6 hours, Bella can print the same standard photo order in 3 hours. We're being asked for how many hours can a single standard photo order be produced. And the big thing is we recognize that if there's a standard order of photos, we can just define the number of photos. So let's say the number of photos is equal to 18. Just that 6 hours times 3 hours. So we'll come on over here and we'll actually create a couple of average circles or rate circles to illustrate what's happening for these ladies. So if we've got Jenna first, we know that the work is 18 photos. And we know that Jenna takes 6 hours. So that should go on the left-hand side. 6 hours is on the left. So that means our rate is 3p photos per hour for Jenna. So then we can just produce a similar situation for Bella. So that's going to be B. It's the same 18 photos, but Bella takes 3 hours. Now, the 3 hours here, if you divide 18 by 3, we're going to have a 6 photos per hour rate. Now, when you're seeking for combined time, this is the one exception to the rules that we talked about in the lesson where you can't combine the rates. Well, if the rates are the rates and they're being done simultaneously, you can actually do it together. So because we are told that our rates are happening concurrently, we can actually go ahead and produce a combined rate circle. So our combo, we still have 18 photos. But now, since the two ladies are working concurrently, we can just say, well, Bella does her 6 photos, Jenna does her 3 photos, so that's going to be 9 photos per hour when they work together. And we can just come over and do our division because we remember in the rate circle that you can just divide the amount of work by your rate and discover that it's just 2 hours. And there is our other approach to solving this if you forget the combined time formula, but I will definitely admit the combined time formula is going to be fastest. So let's close out this lesson by taking a look at an example data sufficiency involving rates as well. So here it's all about translating what you know into algebra. So we know that at CAM's Bicycle Bureau, there's a production order for 300 bicycles. So that's our work. And our work is just equal to 300 bicycles. And then we've got our question, which is, can CAM guarantee that the order will be completed in 2 weeks or fewer? So we've got, is the time less than 2 weeks? And of course, this is a yes-no data sufficiency, so we'll just box that off to make sure we don't lose sight of it. Now, what we need, since we know the bikes, is we've got to determine, is the rate greater than 150 bikes per week? Because we know if there's 150 bikes per week, then you get the 300 bikes completed in the 2 weeks. So always focus on the specific aspect that is necessary. Now, condition 1 says that CAM's Bicycle Bureau can produce a maximum of 50 bicycles per day. So we know the max rate is equal to 50 bikes per day. But if all I get is the maximum rate, I don't actually know if CAM reaches that on a daily basis. It's possible, but it's not absolute. So this by itself, not sufficient, and our options are B, C, or E, because if CAM gets anywhere near that max bikes per day, then he's clearly going to surpass 150 bikes per week, but we don't know whether or not the Bicycle Bureau is capable of that all the time. So then condition 2, however, says that the minimum rate is equal to 25 bikes per day. So that means that if we take that 25 bikes per day and multiply by 7 days per week, well, then 7 times 25, 25 times, or 20 times 7 is going to be 140. 140 plus 7 times 5 is 35, so 175. So we know that our rate is greater than or equal to 175 bikes per week, which is, of course, greater than the 150 bikes per week that we needed. And so this, on its own, is sufficient, and our answer is choice B. So we've gone through a whole bunch of different ways to address rate problems on this exam. Definitely one of the more advanced concepts that the exam likes to use in unique manners. So go ahead and complete some practice rate problems and see which method is best for you on individual problems in your drills.